In this brief lecture, we're going to describe each of the learning outcomes that will enable us to explain the information provided in a phase diagram. Let's start by examining the phase diagram for a substance we're all familiar with. When considering the phases of water, we see that each phase is dependent on the conditions of temperature graphed along the x-axis and the pressure graphed along the y-axis under which we're operating. We see that this will give us several regions under which the solid, the liquid, and the gas phases we're all familiar with are stable. It's important to be able to locate and label each of these phases on a generic diagram. This solid, liquid, and gas pattern will be followed for all of the diagrams we examine in this class. Each of the phases are separated by lines denoting the equilibrium condition that occurs during the phase change. We see the sublimation curve denotes the equilibrium between the solid and gas phases. Removing heat from gas phase water at a certain pressure will cause deposition, a process we know better as frost. If you add heat to ice, as in this picture of a frosty fence in the sunshine, the solid will sublime directly to the gas phase, skipping the liquid phase completely. The fusion curve denotes the equilibrium between the solid and the liquid phases. Removing heat from liquid water at a certain pressure will cause it to freeze. If you add heat to ice, the solid water will undergo fusion, a process we know better by its common name, melting. The vaporization curve denotes the equilibrium between the liquid and gas phases. Adding heat to liquid water at a certain pressure will cause it to vaporize, like you see here above this foggy lake. If you remove heat from gas phase water, you'll see the water condense to the liquid phase. If you've ever taken a cold drink out of the refrigerator on a warm day, when that drink begins to sweat, it's actually the atmospheric water condensing on the cooler surface. We've already seen that water is unique due to its hydrogen bonding, which causes water to have higher melting and boiling points than predicted from periodic trends alone. The hydrogen bonds also cause liquid water at 4 degrees Celsius to be the densest form of water. When water is cooled below 4 degrees Celsius, the molecules arrange themselves in a crystalline lattice that is lower in density, as shown here. This causes the fusion curve of water to have a tilt to the left, or negative slope, which is not what you tend to see in most substances, where the solid phase is more dense than the liquid phase. This is just one more way that water is weird. Finally, we have 2 points of interest. The triple point, where all 3 phases are in equilibrium with one another, and the critical point. Notice that the vaporization curve terminates at the critical point, and we're left with this fuzzy area between the liquid and gas phases where supercritical fluids exist. The critical point is defined by the critical temperature, the temperature above which a liquid cannot exist, and the critical pressure, the pressure at which the transition to a supercritical fluid occurs. Like a gas, a supercritical fluid will expand to fill its container, but its density is much greater than that of a typical gas. Like a fluid, supercritical fluids are able to dissolve certain solutes while exhibiting essentially no viscosity or surface tension. Supercritical fluids find many uses, including decaffeinating coffee. A link to an article in this process can be found in the lecture transcript. To round out our discussion of phase diagrams, let's look briefly at the phase diagrams for iodine and carbon dioxide. We see that both substances have a positive or forward-tilting fusion curve, indicating that their solid phases are denser than their liquid states. This is typical of most substances. Keep in mind, water is weird. We also see that iodine, like water, has 3 stable phases at normal atmospheric pressure. If we insert a dotted line that crosses all of the temperatures at 1 atm of pressure, we see it passes through all 3 phases. If we do the same thing for carbon dioxide, however, we only pass through the solid and gas phases, which explains why dry ice sublimes. All right, it's time for some questions and answers. Which region contains a gas? Region C contains the gas. What process is going on from moving from point B to point C? As we move from the liquid to the gas phase, we are vaporizing the substance. What is the correct label for curve E? We're moving between the solid and liquid phases, so this is the melting or fusion curve. At point F, which phases are in equilibrium? At point F, we're between the liquid and gas phases.